Screen sharing is for.
Sharing. Jo, a klikni. Klikni dovnitř. Tak, a to změní.
Furt je to pauznutý. Tak. Teď se to všichni viděli. Okay. Okay, so I think everything is all set. Right, so welcome everyone. My name is Jindřich Helcl. I work here in ÚFAL, as been said. My office is in Troja. So come and we can have a chat. I will talk about tokenization for natural language processing, and I will explain some difficulties of that. And in the end, you will agree with me that it's a hard thing to do. So in my talk, first, I'm going to spend some time on introducing the problem of tokenization and explain how it's done in neural networks and in NLP in general. And then I will move on to describing our recent paper, which has been accepted to NLP, about lexically grounded subword segmentation. So let's begin with tokenization. So in our NLP models, which are based on neural networks, we need to solve the problem of getting the text somehow into a model which is like purely mathematical, so purely numeric. So if you look at descriptions of neural network architectures, then the things you see usually are mathematical formulas, and the text is not a number. So tokenization is all about getting the text and transforming it into a numerical representation. So, and this example and this sentence, some of you might know where this comes from for bonus points. So we have I think around 8 words, and the goal of tokenization is to somehow transform it into a sequence of numbers, and the numbers are then usually in most of the models are transformed into vectors of real values. But tokenization is all about getting these 8 words into these 14 tokens, and I will explain how it's done. So let's take a closer look on how tokenization works. In our work, we structure it in steps. The first step is pre-tokenization. So in this case, pre-tokenization is basically splitting the text on white spaces and removing punctuation symbols from the words. The usual thing was done in like early days of statistical NLP as well. Now it's done in a bit simpler way. We just really split the sentence on white spaces, and we strip alphanumeric characters from the rest. And then we applied subword segmentation, which means that some words get actually split into smaller units. And this is more or less, sometimes it can seem random, which is one of the things that we deal with in our paper. So here we can see that pre-tokenization gave us like 3 more tokens, and the subword segmentation split some of the words in 3 more tokens. So we end up with 14 tokens, which we look up in a vocabulary. So vocabulary is just a list of tokens, and the tokens have some numbering. So these numbers here are just like positions of the tokens in the vocabulary. So I guess you can see that the comma is like 14719 is like twice there, and I think the rest of the words are unique. So why do we need subword segmentation? So that's this like random random splitting of words. So if you look at the main cause, the main motivation for us is data sparsity. So I've took this statistics out of 50 million sentence corpus, and if you just apply pre-tokenization without subword segmentation, then you end up with a vocabulary of roughly 600,000 different tokens, most of which has the frequency of 1. So if you look at this plot, we have on the y-axis, there's a frequency of the word, and x-axis is the rank in the vocabulary if you sort the words according to the frequency. I guess all of you know this. All of you know this red line. But what happens if you use subword segmentation, specifically if you use statistical subword segmentation, you have a fixed vocabulary budget, let's say 32,000 tokens as in here. And it's done in a way that it reduces the number of the low frequent tokens in the vocabulary. So basically the rare words are split into subwords, and then the subwords are reused more often within the data set. So then when the words are converted to the word embeddings, then when you do the subword segmentation, you encounter each segment a lot of times, unlike when you are using word-like pre-tokenization in which you only encounter the word once, so that, and then your embedding vector will not be updated enough times because these are all learnable parameters of the neural network. So it's good to see all of the segments more than once, basically. Okay, we can also go further. You can also use character level models, but this is they have their limitations. One of them is that individual characters very often don't have any meaning of their own. So you always need to apply some more processing on top of text, which is split into characters. And this is really out of scope of what we are doing. So subword segmentation usually is done by one of two algorithms, Byte-Pair Encoding, BPE, or SentencePiece, or the unigram model. And they both start with the vocabulary. And one is top-down and the other one is bottom-up. In Byte-Pair Encoding, we start with vocabulary of just characters. And in contrast with SentencePiece, we start with a very large vocabulary, which is composed of various substrings of words. And then we kind of make our way to our predefined vocabulary budget. So in case of Byte-Pair Encoding, what we are doing is that we merge the subwords which form the most frequent pigram in the data, and thus increasing the vocabulary size. In SentencePiece, we throw away subwords which has the least impact on the unigram loss, and thus reducing the vocabulary size. So these methods kind of converge to the same vocabulary size as the algorithm proceeds. So what are the problems with subword segmentation? So I think you can see this on this slide. So it's not really consistent. So sometimes when you use different form of the same lemma, the root gets segmented in a different way than it would be segmented in a different form. So it's like you can see it in the word looks here. You can see that it's not very morphological. So I guess the word kumbalu is not really divisible into smaller units as well. And the same goes to the word looks. So these are the issues we try to tackle in our paper about lexically grounded subword segmentation, together with Jindřich and I. And okay. So the motivation of this paper is to have subword segmentation, which would be kind of morphological in the following way. So first, we would like to have the splits between subwords to be on the boundaries of morphemes. So something like maybe this for netopír. You can also have netopíři, so the morphological split maybe is there. But of course, we want to keep the property of the statistical subword algorithms, which do not split words which are frequent enough, because we can see them a lot in the vocabulary. So we don't want to necessarily split everything to individual morphemes. So an ideal example would be on the left-hand side here, where we do like 3 splits which are on the correct positions, as opposed to the case on the right, when there is lots of splits, and many of the splits are on the positions which are not morpheme boundaries. So, and we evaluate how good a segmentation method is using the precision, which is the number of correctly placed splits divided by the number of total splits. And we have two research questions in these papers. First one is, can we achieve better precision using lexical features from embeddings? And the other question is, if we can achieve this, does this lexically grounded segmentation actually help a downstream task performance? And we will see the answers to that at the end. So we formulate the problem of tokenization like this. So first we apply the pre-tokenization, which is split words apart from punctuations, and we split words on white spaces. We call that word-like pre-tokenization. Then there are two methods how to construct the vocabulary. I was talking about it as well. It's Byte-Pair Encoding and unigram language model. And then for the actual inference, you can use the same methods of Byte-Pair Encoding and unigram SentencePiece. So we have three contributions to this scheme. One thing is we propose an alternative way of pre-tokenization with Morphessor. Another contribution is we propose a new inference algorithm for word segmentation, which is based on subword embeddings. And then we propose an upgrade on the segmentation algorithms, which uses bigram statistics. So let's go step by step according to these three items. So first, we apply Morphessor for pre-tokenization, so Morphessor is an unsupervised morphological analyzer. So the input is a word, and it will give you a set of morphemes in that word. And when we use this, we run Morphessor after we pre-tokenize using the word-like pre-tokenization. So it looks like this. First, we have the sentence, and then we pre-tokenize it as in the beginning. And then later, when we use Morphessor, it'll add some splits about which we are fairly certain that they will end up at the correct positions. Then the other, and perhaps the most interesting addition to this is a segmentation method based on subword embeddings. So probably you are aware of word embeddings, but let's just summarize. So we have this. So this is a formula which expresses the skipgram model. We have the probability distribution given by normalizing the embedding matrix, the multiplication of the embedding matrix with the output embedding matrix W. This is learned in the model, and this norm of C is the word co-occurrence matrix estimated from a data set, and when you normalize it, you get this distribution out of the softmax model. So you can see that the distribution of the model reflects how the words interact with each other in the data set. And you can plot then the matrix E in 2 dimensions, and you will hopefully get something like this. So words which are similar appear kind of together in a single place, like this kumbal and kumbale have like very similar meaning, and skříň as well. You can see that upír is like somewhere in the middle of vysavač and netopír, and so on. So we are kind of happy with this word embedding representations in 2D space, but we would like to have subword embeddings which would fall into the same vector space. And we propose to do it analytically with this formula. So we can keep the W from our word embedding model, and we introduce this matrix A, which simply means which subwords belong to which word. So this matrix A is just zeros and ones, and one is at the row of a corresponding to a subword, and a column corresponding to a word, and where the subword is a part of the word. So by multiplying these two, we get a subword word matrix, co-occurrence matrix. So it will tell us how many times a subword in one word occurred in a data set with like in a neighborhood of a different words as well. And then we can solve this equation for ES, which is the only unknown. And we see that if we just take the logarithm of this normalized matrix multiplied by the right inverse of the output embedding matrix, we can get the embeddings of the subwords, which will fall into the same vector space. So we hopefully see something like this. So subword net op, which is a part of the word net op, appears close to the word net op, and on the other hand, subword ne, which is also part of the word net op, is kind of far away because it has other meanings as well. So then when we have this subword embeddings computed, the only thing we need to do is compute, or when we want to assign a segmentation to a word, we need to find subwords when we put them together to like make up the word again. So we want to do this in such a way that the overall distance of all the subwords to the word is actually minimal. So we just measure the distances of all the subwords we can use, and using dynamic programming, we can segment the words using the most similar subwords. And because this method can provide us with subword embeddings for all the substrings of the words in the data set, we actually initialize it with either BP or SentencePiece segmented data set, so we have less subwords in the beginning, and then we iterate recomputation of the embeddings, and then we resegment the data using the new embeddings, and we do this in like 20 epochs to refine the embeddings and the vocabulary a bit. Okay, the last contribution of the paper is the bigram model. So once we have a segmentation method, it doesn't really matter if it's the embedding method I was talking about, or if it's just plain BP or unigram model. We can segment a data set using the method, and then we collect statistics about appearing bigrams in data set, and then we can segment the words by minimizing or maximizing the bigram probability of the bigram language model. So we take the dominoes and we can just assemble them like this. And the advantage is that unlike when we apply it to the embedding-based segmentation, unlike that method, we don't need to run morphesser during pre-tokenization, and we don't need to store the large embedding matrices during the inference time. Okay, so let's look at the results. There is lots of numbers, so I will try to make it as clear as possible. So first we evaluated the segmentation methods intrinsically on a sigmorphon share task on the morpheme boundary precision. So we tried that on 8 languages: Czech, English, Spanish, French, Hungarian, Italian, Mongolian, and Russian. And first we can see that when we use, so the more yellow it is, the better is the number, and the blue is like the other way around. It's a script which is called from LaTeX. So the first thing we can see is that morphesser gives us better. Now, when we use morphesser for pre-tokenization, we end up with better numbers, which is to be expected because we already made some splits on the morpheme boundaries. So the top 2 like chunks are more blue than the bottom ones. Then we can see that when we compare SentencePiece to Byte-Pair Encoding, which are these 2 segmentation methods, we see that the unigram SentencePiece is better for vocabulary construction if we use it with just word-like pre-tokenization. Next, we can see that when we use embeddings for the segmentation, it's better than if we don't do it, which is good news. And lastly, we can see that in this intrinsic evaluation, the bigram model is slightly worse than using just the embeddings models, which is also to be expected. Okay, next we evaluate our methods on part-of-speech tagging. We use the same languages as for the intrinsic evaluation, except for Mongolian, which was not available in the dataset, we evaluated on universal dependencies, and we trained the tagger, which was a small LSTM network for all of the languages in all of the settings. And we can see that when we are using subwords at all, it's like much better than using just the words with large vocabulary or just the morphemes. Then we can see again that using Morphesor for pre-tokenization also helps, especially for Hungarian, which is all out of these languages, it's the only one which is agglutinative and highly morphological, which is also a nice result. We can also see that the segmentation we propose is consistently better than the rest. And the best results were achieved using Morphesor pre-tokenization, Byte-Pair Encoding, and segmentation based on embeddings. Okay, next, we evaluated on machine translation on 18 different language pairs, and there's like an awful lot of numbers, but we can luckily average them over languages and normalize the score. So we end up with this little table from which we can see that Morphesor does not help, our model does not help, and it only helps where it's already broken by Morphesor, so it helps a bit. And that the best way to segment your data is just to use SentencePiece or Byte-Pair Encoding, the old statistical methods with no extra addition. Okay, so to summarize, can we achieve better precision using lexical features from embeddings? Yes, we can. When we use it, does it actually help our downstream tasks? No. So is everything lost then? I think that not. Specifically with the frustration from the machine translation task, I've been pleasantly surprised by the attendance on this year's ACL Birds of a Feather session on tokenization, where we've actually found out that it's not just us, like all of the people are always trying to come up with better ways how to segment data so it makes sense, but they are always failing on the downstream task, or at least they have the same results as not bothering at all. So that's why we decided to propose a workshop on ACL on tokenization, which hopefully would attract some papers and people would know and people would have place to share their frustrations about problems with tokenization. It's organized by us, Tomáš, Jindřich, and me from Charles University and 7 other people from 7 institutions. And we are going to need reviewers. So if you want to help out, you can join this tokenization workshop channel on Slack and we will get in touch when it's time. The workshops due for the proposal were in the beginning of the month, and I think we will know in 3 days if it's accepted or not, or maybe in the end of the month. Yeah, I think I saw 23rd somewhere, but I remember we talked about the last of October, but it's going to be soon anyway. Okay, thank you. That's it for now.
Yeah, thank you very much. And also thank you for the courage in a way. Now, questions? Linguists, wake up.
So for the translation, is there like any success story at all with someone finding a tokenization that helps downstream?
Yes, those would be. Oh no, it's too far away. Those would be these 2 methods.
But past that, nothing.
Yeah, past that, I don't think there is anything worth mentioning.
Okay.
Yeah, so why is that so, if I may? That's what is your explanation that downstream
What's your
empty
moment?
all Yeah, Andre, here's Andre, just from next door. I was
Andre
wondering,
is
what is
assistant in the
your
office.
Moment, I need to turn on.
the loudspeakers? So
Okay,
am
you
I
can
audible
speak.
now? Yes, yeah. Thanks for inspiring talk, and I would not say like warning talk, but yes, it's um, the persistence is something that we should learn from you from this experience. And my question was simple: what is your explanation that it never helped in the downstream MT? I also have a paper with Dominic some years ago where we didn't get any useful gain from like focusing on tokenization.
I think the main reason why this does not work on like MT specifically is that MT is like very large scale problem,
Yeah.
and you have a lot of data and it's just
Yeah.
robust. And it's the same reason why I think it's not going to help for large language models as well. But I'm still kind of hopeful and that we will collect a good research in the workshop.
I have the same explanation for things. Yeah.
Okay. I have a quick question. Have you tried the tokenization on other than European languages like Chinese, where there's no explicit word separation, or do you know other groups that were trying it, and did they also were unsuccessful on these languages?
Yeah, I think that the vibe we got from the Birds of a Feather session at ACL was that everybody has the same issues. I think there might have been some languages in the MT language that we tried, but I'm not sure. And actually, it doesn't look like so. Is there? But yeah, you know, because we've done it together. Yeah.
If I understood it correctly, you are using precision
Yeah.
as the metric. Isn't that wouldn't like F1 score would be better, or like because precision doesn't capture everything like?
Yeah. So the reason we use primarily precision is that with subword segmentation, you kind of want frequent words to stay in the original form. So if you don't need to split them, you don't split them. So you are kind of limited by the vocabulary budget you have. So you need to do some splits. So the precision is all that matters. But we report all of the scores in the paper if you want more details.
Thank you.
Okay, so you sort of answered one of my questions whether this will help or not help LLMs, but you said probably not. But have anybody tried? And then I have another question.
I think yes, but I'm not aware of, like, the only thing I like remember is that I know that the people complain that they tried, but maybe it's like unpublished because it's a negative result and it's hard to get it published.
Okay. And now what about multilingual LLMs? Would the the tokenization would be done completely separately, or how that would work?
So for multilingual segmentation, it's kind of even more interesting because if it was like morphologically like plausible, then you would get morphemes which would align to each other. And so that's the work of Jindra and Kathy and Tomáš Limiševič from this. Was it accepted? Or no, you sorry. It's submitted. It just submitted last week. And also Tomáš is devoting his work to multilingual models. And yeah, I think like there's a potential for it to help, but so far there are no such results which indicate so.
Okay, one more question, please. Have you tried also some supervised methods? Because all of those basically are like unsupervised. So like training on some linguistically motivated.
No, we haven't. Or at least I'm not aware we did. And I forgot a lot of things. But Indra is nodding, so we haven't.
Thank you.
Well, it's unclear where to get the data because you have the test sets from the Sigmorphone share task, but you.
Oh, I can talk to you after the.
Okay.
So nobody in the Zoom? No. So let me thank you too for your presentation. I think I can speak on behalf of all of us that we keep our fingers crossed.
Thanks.
And as for the